before we move forward and create our first tensor operation, I want to recheck this shape, and you can see that we return a tuple. Yeah, and in case if we, for example, just change our data to add one more dimension like this, you can see that we have tuple with two integers, first dimension and the second one. Let's import the data type tuple, and we need to return the tuple of integers. And when we set up the data like this, I want to preserve the data type for our tensor data. So let's revisit this data, and we need to put as the second parameter to build the array, we need to add self.data type, just to preserve the data type for our property data. And one more fix, we have this data type and we include scalar, list and numpy and the array into this union. And also we can add the tensor, because our build and the array receive the data, and inside we work with this data type and check the instance of tensor. And in case if it's a tensor, we return numpy array with the data from the tensor. So I think that it's the last piece that we need to fix. The backbone of the tensor is basically useless. It's just a mechanism above the numpy array. But now we can track the dependencies in the list and compute the gradient for the whole list of the dependencies. I can show you the example of the fundamental operation in the tensor, the transpose method. To implement the transpose in forward and backward mode, we don't even need to go into the calculus. So let's define the transpose method, and we have self, of course, and we also have the access property as the tuple of integers, and we need to return back the tensor. And first we need to transpose the data inside the tensor class. Let's create a variable output, and we need to call numpy.transpose, and we have self.data. We receive the data in this property. As far as I remember, we implemented it like this. Yeah, we return the self_data that we keep inside the tensor. And we have the second parameter, access. Let's just provide this access directly to the numpy transpose. And the second piece that we need to build, it's the dependencies. Let's implement the dependencies as the list of leaf. By default, it's just an empty list. Inside the leaf, we track the current node in our gradient tree, and we have the gradient function that we use in the backward mode. We need to define the method backward, and we receive the gradient as the numpy and the array, and we return the numpy and the array. Okay, and we need to do the same. Yeah, we need to transpose the gradient. Yeah, so when we need to return numpy transpose, but instead of the self data we need to put the gradient. When we go forward and transpose the tensor, when we utilize the backward mode, we need to do the same, yeah, because we change the data shape, yeah, with this transpose action. And we have a flag. This requires gradient. And in case if our tensor requires the gradient, we need to add to the dependencies list. We need to append the leaf, and we create a leaf with the value equals self, because we track the current node in this case. And for the gradient function, we utilize this backward. So I think that this leaf consists of two properties that we need during the backward mode computations. As the last step, return the result, and as the result we return a new tensor with the output value and with the requires gradient, as the self requires gradient, and dependencies, we use this dependencies list. Okay, and I think that this implementation works fine for the forward and for the backward mode. Let's also define the property T, yeah, with the self, and we need to return the self dot transpose in this case. Okay, and I think now it's approximately the same API as in PyTorch, yeah, or is in the NumPy. Let's reinitialize this tensor class, and now we have this example, basic example, yeah. Let's check the tensor. Okay, and it looks like the tensor was the same data as we put right over here to the data setter. Let's call the property transpose, and we have a small trouble, yeah. Tensor transpose missing one required positional argument, axis. Let's init as the none, this axis by default by none, and reinit this class and rerun this code. Okay, and looks like it works as we expected, yeah. It's the fully valid transpose operation. We can run it twice, and as you can see, it just cancels out the previous transpose, because the transpose of the transpose, it's the same matrix. And we track these dependencies in the list. So how can we run the computation of the gradient? And we need to implement the backward method that implements reverse mode automatic differentiation using the chain rule of calculus. What is the chain rule? And if we have a function composition like this, yeah, we have this format f of x equals g of h of x, we solve it by the chain rule. So it's something that we need to implement, and we do this in the backward method. We implement this chain rule of calculus that solve our computation graph. We need to define a method backward self, and as the second argument we have the gradient. It's an, let's say, optional parameter as NumPy and the array. Let's init with the none by default, and we return none because we just compute the gradient and return nothing. We gonna use this gradient for the internal computations. We can utilize this for the stochastic gradient descent or any other type of optimization algorithm. Okay, first let's check if we have no self dot requires gradient. It means that we do something wrong, yeah, because we need to track, we need to install this requires gradient flag to true for the tensor to track the dependencies list. Otherwise, we just won't do this, we just won't append the dependencies to the list. We just raise the runtime error. You cannot call backward on a tensor that does not require gradients. Yeah, if you need gradients, just ensure that this flag equals to true. Yeah, otherwise just error. As the step number 2, we need to initialize the gradient. If we have no gradient, gradient is none, we need to check the shape, the gradient dot shape. If our gradient shape just an empty tuple, it means that we work with the scalar, and the gradient of the scalar is just 1. We can init the gradient as the, let's say, tensor build ND array, or we can call numpy dot array of 1. Yeah, we just initialize the scalar value inside our gradient. Yeah. Otherwise, if our gradient shape is not just empty tuple, it's not a scalar, we need to raise a value error, because you need to provide the gradient if tensor has shape. It's very necessary, yeah, and you will see why for the next step. And for the next step, we need to accumulate the gradient. So let's add to the self.gradient, let's add the gradient that we receive as the argument in our backward method. We just contribute for the current node the gradient that we compute on the previous layer. And then, as far as I remember, we have our dependencies on the level of the node. And you can see how we append the dependencies. For the value self, we have this backward method that transpose the gradient for the next computation. Yeah, we compute the backward pass, we prepare the next gradient step and push it to the next layer. And that's where we utilize the chain rule of calculus. Let's make a loop dependency in self.dependencies, and we call let's create a variable backward gradient, and we call dependency dot gradient function. We contribute this gradient that we receive as the argument of the backward to the gradient of the current node. And we need to compute, we need to run the backward step and push right over here the gradient that we receive for the backward step, yeah, because we still on the same level. We can equally contribute this gradient for every dependency in the gradient graph. So we compute the new backward gradient, and now we are ready to make the recursive call. We need to call the dependency dot value, and we need to call the backward for the value inside our dependency. Yeah? And in this case, we provide the backward gradient. Take the dependency, take the value, and run the backward for the value. It means that we goes backward in our computation graph. And I think now we have the fully implemented backward step for the computation graph. Let's run this cell and then come back to the example with the transpose. Let's switch the required gradient to true, and now we have the transpose action. Let's create a variable t T underscore capital T and run the T underscore capital T dot backward. So we can run the backward computations for this T underscore capital T. We need to provide the gradient numpy dot once-like and T underscore T dot data. We create the gradient as the full set of ones for the current node and run the computations in the backward mode. Everything works fine, it looks nice, and now we are ready to track the gradient for every node. Let's say that we track the gradient for the small t and T underscore capital T. And here we go. It looks very nice. We have the gradient for the transposed tensor, and it works fine. Yeah, the shape looks perfect. And when we call the gradient for the original tensor, it's in the right place. Yeah, we have the shape exactly as we have for the tensor data. It means that in the backward mode we have the valid computations. Yeah, we push the computed gradient to the next step, and we rotate the matrix. Yeah, we rotate this data. Everything looks nice, but it's not something conventional. We can't create like a neural network with only transpose. We need to implement more operations for our tensor to build something more significant and build the real training loop.